Right, so I'm Yzelman from the Huawei Research Center in Paris. Maybe I should say a little bit first about the research center that we have there. It's relatively new. Our group in particular is focused on parallel computing in general. Some of our work, some of the projects that we have been undertaking has to do with graph computing, hence on the invitation of the organization and two connections of Yzelman, I got invited here, so I'm happy to be here. I'm slightly normally outside of this community, as you can probably see from the title. So my background is more in high performance computing. So what I will do in this talk is first summarize the kind of techniques we use for sparse matrix computing, how to get that as fast, as efficient, and as scalable as possible. And then I will try during my explanation of these techniques to bridge this also to graph computing, like how are we going to try and apply the same kind of techniques to graph computing. So from a sparse matrix perspective, this is kind of like the slide I use in standard to explain the problem. Because normally what you may have is, if you have a sparse matrix, it might have a clear structure. So for instance, a couple of diagonals, things like that. But in practice, and certainly if your problems come from graphs, you will see a picture like this if you try to make a plot of the graph. So I call these types of matrices unstructured. So what I will do during this talk is basically describe techniques how to speed up computations on these types of matrices. And as a secondary point, I will also talk about how to make some of these techniques more usable, which is especially relevant for graph computations. There are a couple of standard problems that you have with sparse matrix computing. If you just focus on a single node, then the problems that you have to do with caching, efficient caching. And I will explain all of I will go a little bit deeper on these points. So inefficient cache use, that is one. The other one is that we have limited memory bandwidth. If you look at the development of architectures, you can see that the flop rate, the computation speed has been increasing tremendously over the last couple of years. And so, I mean, the clock speed of a single core in the last couple of years has no longer been increasing, but you still have like multiple cores appearing on the same processor. And if you aggregate that, then still you see a similar kind of increase in processing power. But one of the larger problems is that the memory bandwidth has not been keeping track with these developments. So if you look at especially the memory bandwidth per CPU core that you have, you are quite limited, and it has been stagnating over the last couple of years. Another problem is non-uniform memory access. I will only touch a little bit about that. It has to do with data placement. If you go to distributed memory, then the main issue you face is that your network might be inefficiently used. So too much data is being moved around in an inefficient way. I gave both of them the same color, the blue color, because actually it turns out that inefficient cache use in a shared memory case is very closely linked to too much or inefficient data movement in the distributed case, and you can use similar techniques to try and attack either problem. Okay, so the problem of inefficient cache use I here illustrated on a very tiny sparse matrix, a very tiny graph, which are equivalent statements. But of course, you can imagine this also takes place on much larger graphs. So for instance, if I take, as is normal in scientific computing, a row major or column major ordering of the non-zeros in my sparse matrix, in this case row major, then all the accesses on my output vector are contiguous, so we have no cache misses here, but you start jumping around on your input vector, and this is where you lose cache efficiency. Because you start reading in elements from the input vector, at some point you start pushing them out, whereas later in the matrix you need the same elements again. So this is a problem. we solve that? So there are multiple techniques proposed, and this picture actually visualizes several of them. So, especially in the dense case, what people tend to do is blocking of the sparse matrix. So those are these black squares that we have here. Unlike in a dense case, blocking alone is not enough to get good cache efficiency. One way of getting better cache efficiency is actually to employ space-filling curves throughout of these blocks, and you can also apply them on the non-zeros themselves, of course, so that we take block size equals 1. But in general, you do that on the blocks themselves. So the advantage of this kind of ordering is that if you imagine your input vector, let's say on the top of this picture, and your output vector on the side of this picture, then as long as you follow this curve, you are local, kind of, both in the input and output vectors. Right? So as the computation progresses, you exploit better the locality on your vectors. If I relate this back to graphs, then this means that you are reordering basically the edges of your graph, how you store those edges in memory. So that is one technique. Another technique is to not reorder the non-zeros themselves, to not have a different order of the non-zeros, but instead have a different order of the rows and columns of the sparse matrix. So again, if I try to link this to graphs, then basically you are reordering the order in which you store your vertices. Right? So those are the two different analogies that you have here. One good way of doing this is by employing hypergraph partitioning. So I kind of plot here, like on the left is a reordered sparse matrix, and on the right there's the hypergraph representation of the same sparse matrix. The advantage of using hypergraphs here is that you can exactly model the amount of data movement. If you were using graphs instead, you would not be able to directly model it. So in this case, we can say that we are optimizing or minimizing, I should say, the data movement during, well, in this case, sparse matrix factor multiplication. Of course, one question would be how quickly, or what is the effect in practice if I do all of these things. So on the left, I have a link matrix from the Stanford web pages. On the right, I have I think it's it's a two-dimensional reordering in 20 parts. So you can see, while the original matrix seemingly has no structure, well, everybody here, of course, knows that link matrices definitely have some structure. This structure can be exposed and can be exploited during computation by doing partitioning and reordering. So that is what we have here. So the gains that are on the bottom is about 50%. I think actually I also had gains so I skipped over that, I'm sorry. So when we do the reordering of the non-zeros themselves, then we also see clear gains. So this is a row major ordering, you get 345 milliseconds on this matrix on a single core, right? So this is a sequential computation. If you do the Hilbert curve on the non-zeros themselves, you can see you gain a lot. The downside is, of course, that you need to do a sort on all of your edges to get them sorted according to this Hilbert curve. You can offset this cost by doing blocking, and then you get this result over here. So both techniques are effective in speeding up computation, and moreover, they are orthogonal, so you can apply both. You can like reorder it in this fashion, like the rows and columns, and after that you can also start and reordering the edges in each of these blocks separately, so you can combine those two things. So that is like a broad overview of how we can deal with cache inefficiency. The other problem on my list was bandwidth. So what has become somewhat popular in scientific computing is this roofline model, as people have come to call it. So on the horizontal axis, you have the arithmetic intensity or computational intensity of your algorithm, and that means how many operations am I doing per byte. On the vertical axis, you have the attainable performance, depending, of course, on the CPU that you are using. The idea is that if you do a lot of operations on relatively few data, then you are compute bound. Your CPU does not have to wait on data to arrive on your CPU. So that means you're on this side of the curve and you hit the computational groove. However, if you have relatively few operations per byte of data that you need to operate on, then of course you become bandwidth bound. You need to wait on this data to arrive at your CPU before it can do anything, which means that you are on this basically diagonal part of this graph. So the bad news for sparse computations is that of course you are completely on the left of this picture, right? You're completely bandwidth bound, although in some architectures you're also very much latency bound, but I will not go into that in this talk. So I put some turnover points on the bottom there. Another good point is vectorization. So vectorization, vector widths have been increasing on recent architectures. But if you look to sparse computations, then in theory at least it shouldn't matter, right? Because vectorization basically causes your computational roof to lie a little bit higher. But for sparse computations and graph computing in general, I suppose we are completely on the left end of the spectrum. So vectorization, if you assume this model at least, should not matter. But again, so if you care about memory latency, then sometimes you do see an effect if you do vectorization. Okay. So what is the consequence of that? The consequence is that you need to apply compression on your data structure. So every byte that you save on your storage will immediately lead to an increase in performance because you have fewer data to move for your computations that you are doing. So one of the simplest way of storing your data is simply to use a coordinate format storage. So for every edge that you have, you store the coordinates of that edge, so the vertices to which it connects to explicitly. So if you do that, then you have a storage of 3 times the number of non-zeros over here. If you use the standard format of what is the de facto standard in scientific computing, it's either compressed row storage or compressed column storage, or CSC as it's also known. Then what you save is basically the array that you would need to store all of the row indices, because now you sort everything per destination or per source, so your storage becomes 2 times the number of non-zeros plus the number of vertices that you have in your graph. Thing is, if you do that, of course, so if you store things in a row major fashion, then you can forget about one of these earlier cache optimizations that I talked about, namely the reordering of the non-zeros according to the space-filling curve, right? So you get compression, but you lose an opportunity to optimize your cache use. So in fact, you need to think about smarter ways to store your data that do both compression and are able to have an arbitrary order on the number of, on the non-zeros of your sparse matrix, for example, according to this Hilbert curve. So that indicates that it is a difficult problem if you take into account these many different aspects, or otherwise, in that you will see no gain of applying some of these techniques. Some more remarks on what you can do with this data structure. So we actually published this data structure, I think in 2011. One of the first questions I got was, well, can we do vectorization? My response at first was, well, is it useful? It turns out on some architectures it is useful. And then a couple of years later, we indeed fitted that kind of stuff also into this data format. So it's possible. Of course, it's important, like I just said, to do compression. We can do blocking with this data structure as well. And we need to have these arbitrary orderings of the different concepts. So it's all okay with that data structure. So here I have briefly a slide on non-uniform memory access. So as you probably know, many of current nodes that you can buy have multiple processors inside of them, so multiple sockets. This of course means that each of these sockets have local memory banks, right? And the communication between one such a socket and these memory banks is relatively fast, but the thing is, if you go outside of the socket and refer to data, in this other memory bank over here, so you go diagonally, so to say, then the performance that you get out of it, the bandwidth that you can get out of that is much lower than if you do things locally. Of course, you have the exact same problem. If you look at distributed memory computing, you have multiple nodes, there's a network in between. If you stay on your node, you're faster, of course. If you go over your network, you're slower. So also this kind of fact about your architecture has a consequence, namely you have to be careful on where you put your data. So and you can do that in multiple ways if you have if you do sparse matrix computing. So what I sketch here is a one-dimensional solution. So you have a sparse matrix. You say, well, okay, I need to write to my output vector. So if I do things in one-dimensional, it will probably make sense to cut it horizontally because that way I avoid write conflicts, right, on the output vector. There are no two or more processes that need to write to the same output vector element. So that is one way of doing things. So we have here an illustration of two processes doing all of the optimizations that I've talked about locally, so blocking, overcurve, all of that. Of course, one of the consequences is that all of the processes, so if I have 2 or 40 or even more horizontally or vertically, all of those processes need to access the complete input vector. So that is one consequence that you have. And if you take into account this previous picture that I have here, that means that the matrices and output vector parts are can be locally allocated, so in the local memory banks or in the local nodes, but the output vector has to be synchronized over all of the different memory locations that we have. So can we solve that? Yes, we can. And then you enter basically two-dimensional distributions. And these are easy to illustrate with the help of the reordering that I introduced earlier. Because for instance, even if I have 4 parts with only 2 processors, I can still say, well, okay, the top left part I assign to processor 1, the bottom right part I assign to processor 2. And then you see, okay, there's only this part over here where I need to write, where multiple processes need to write to the same part of the output vector. And over here is the only range where multiple processes need to have input from the same elements of the input vector. So you explicitly, during partitioning, you explicitly try to minimize the communication that you have in both the input and output vector. Okay, so again, some practical gains. So this is the Wikipedia link matrix. So sequentially it takes almost 500 milliseconds per multiplication. If I do a one-dimensional distribution, so I do things like I just cut it up horizontally, I go to 21.3 milliseconds. If I do things 2D, it goes to 20.7. So it seems to not matter too much whether you do things 1D or 2Ds. But the thing is, this is on one machine. So this is 40 threads. I think that is a 2-socket machine with 10 cores each with hyper-threading turned on. The speed up, by the way, although it's 22x versus 40, which actually, I think this is a 4-socket machine with 10 cores each with hyper-threading turned off. The speed up of 22 is actually pretty good for sparse computations. What is interesting, what I want to point out here though, is what happens if you increase the luminance, if you increase the number of machines or the number of sockets that your machine has. And this I illustrate here, and you can clearly see that if I go, so this was a slightly old machine, this is an 8-socket machine, so it's still a shared memory address space. But you see that in terms of parallel efficiency, the 2D method behaves a lot nicer than this 1D method, which all but levels off from results here to here. So the point of this slide is basically that if you work on very large scales, you really want to do 2D kind of partitioning to achieve good scalability and good. Okay, so now I'm gonna try and link it to general graph computing. Because what is it that we want? So we have all of these techniques. So my point is kind of, we know how to get performance and scalability, but now we want people to use it, and possibly also people from the graph computing community like yourselves. So The graph class it's an organization that has this as explicit goal. So to do graph analytics basically in the language of linear algebra. So I have a slide, just one slide about that after this one. What we also want to do is we want to be interoperable. So the software that we develop that does all of this in a usable fashion needs to be callable from whatever platform that we have. So now, like yesterday, Yzelman talked about AWA, so that is one. It would also be nice if you could call it from Spark instead. So you write in your native tools. You do the things that you use the tools that you're used to, right, to help your own productivity. But you can still rely on kind of HPC techniques whenever the situation calls for it. Interoperability with classic HPC, I won't talk about, but that's another goal that is nice. I have a couple of references in the below if you're interested in learning more. But yeah, so I'm almost out of time, so I'll just very quickly go through this. So the idea is, like in normal sparse computations, use normal numerical multiplication, normal numerical additions. The idea is, well, it doesn't really matter what these operations really are. You can replace numerical addition with something else, like taking the minimum of some value, and you can take something else in terms of, instead of the multiplicative operator, like for instance addition or the maximum or something like that, as long as there are some certain rules being followed. So it has to have an identity, things need to be associative, things like that. But if you can guarantee that, then in a sense, linear algebra just works, and we can use the same optimization techniques that I just sketched in all of these different situations. So this is how we like to bridge this to general graph computing. Yeah, this is a slide about bridging HPC and big data. So platforms like Spark, they are in a sense automatic, data-centric. So you kind of program in a sequential fashion, but the data is distributed and communication happens behind the scene. This is actually a pretty old idea, so it goes back to, well, someone mentioned BSP yesterday. It goes back to Valiant in the 1990s in his paper on BSP, where he calls it basically automatic mode versus a direct mode, where the direct mode is more like classic HPC. So what we want to achieve is we basically want to achieve that you can program in what looks like to be normal Spark, but you go back to an HPC code in the backend. So, and this is one application that we have. I run it here. So we did multiple things, but I just keep to SPMVs for simplicity. So we here have 100 million non-zeros. So these are 100 million edges in terms of graphs. So if I do that in pure Spark, I get a performance of 27 seconds. If I do that in the code bases we already had, it's 28 milliseconds. So this is a huge performance difference. Now, if we use the bridge that we have developed and basically use normal RDBs to pass down the matrix and the input vector down into our bridge, which does some computation in a HPC fashion and then gives the result back as an RDB, it takes 430 milliseconds. So there is some overhead in this call because data needs to stream in to the HPC backend and back again. And of course, this also means that if you have larger applications, like for instance, complete page rank, then this overhead becomes less, of course, because you stream the data only once, while your computational part of the whole timing increases. So we expect that for real applications, this difference that you have here between the bridge and the actual high performance application draws closer and closer. So yeah, then my conclusion is yeah, as you can see there. So this is basically a simple idea. We want to use all the techniques that we know and have for sparse computations and see how they do on graph computing. There are some future work aspects that might be of interest to you as well. So for instance, I've heard hypergraphs being mentioned multiple times. That's also one of my personal interest, to see how those fit in into these kinds of frameworks. So we know, for instance, that if you have a graph, they correspond quite directly to sparse matrices. hypergraphs correspond quite directly to sparse tensors. And so in that area, you have a lot of exciting work in the area of machine learning. So this is one of the things we think will be really important in the near future. Okay, with that, I'd like to wrap up.
Thank you. Any questions for our gentleman?
So in terms of usability, can you give just rough numbers of how much time is being spent for preparing the data in such a way that it's optimal for processing compared to the actual computation time?
Oh, sure. So the reason why we still use 1D methods is because the pre-processing time there is a lot lower, so it's almost negligible there. It's the same as sorting your data, basically. But for 2D methods, the story is completely different. So if you want to do complete hypergraph partitioning, like for instance we had the Wikipedia matrix as an example on a couple of slides back. Well, some hypergraph partitions, the one I was using is called Mondedan, are sequential, and it takes a couple of hours to do the partitioning. So you really need to make sure that either in your view application your sparse matrix structure always is the same or whatever, or you do really a lot of sparse matrix factor multiplications to make this investment worth it. So this is also why the first bullet there is actually to find methods to do faster partitioning or to alleviate these costs in a different fashion, because we need to do this. If you really want to work at scale, you want to use 2D methods, but then partitioning needs to go as fast.
Further questions? So, I have a question. So these sparse matrix representations basically store the non-zero points. So in a compact format. So in a sense, these take the form of kind of posting lists or of some kind, or lists of non-zero points in a particular order, as you kind of described. Is there a big difference to the way data is stored in graph systems that do not take this matrix abstraction for the connectivity matrix, but just store, let's say, the list of edges? Because in both cases you are down to a list of edges essentially.
Yeah, so if you have a graph and you store it as an adjacency list, it's completely equivalent to this row major order that I described, so compressed row storage. So that is equivalent. The data structure that we have illustrated kind of looks like this. So this is completely different. But here the question is kind of how do you support efficient graph operations on a data structure like that? And that is also still ongoing work, because one of the major differences that in graph computing you work a lot with sparse vectors. You work with a set of vertices.
But why is this representation so terribly different? So this is a lot more like a kind of a semi-blocked version of that list.
It's a block version, but it uses
like
incremental encoding. So you have a start precision in your block, and you jump from block to block, or from non-zero to non-zero, where in this example actually every non-zero is a block of non-zero.
Okay, so but to take the analogy further, I mean, you could store this list of edges in a particular blocked order. I mean, this is kind of, this is what happens if you do data clustering.
Yes.
And then, indeed, inside those blocks, you will find that the coordinates of the list are kind of restricted to the block because they stem all from the same block. They are clustered, and then you can compress those. You can use compression techniques to make those numbers smaller. So there is still. You say it's totally different, but if you apply clustering and compression, you still end up in those systems to something quite similar, don't you?
Well, I will have to look in more detail, but I mean the key point is basically as long as you can guarantee that you're equivalent or better then a simple adjacency list storage,
Yeah.
while allowing for all these arbitrary orderings of non-zeros and blocking and whatnot, then you're good. So as long as you can prove that, then it's
Okay.
then it's fine.
And are these like things also, I mean, do you plan to really use them in a system? So, I mean, it sounds more like you do standalone benchmarks, but are there also, can you also use it like in a generic system where you lots of...
Yes,
lots of-
that is the plan. So
Okay.
the presentation that Yzelman gave yesterday, that is the system there where this work will